So, welcome back students. So, let us go to the next class of this linear vector space. In the previous class we learned a very important concept of dual space and also learn how to define the inner product. So, if alpha is a vector and beta is another vector, then essentially alpha beta is defined as the inner product, and this value is essentially alpha I star beta I equal to 1 to n if this is n dimensional vector. Now, another important thing we also mentioned in last class, that this structure in n-tuple notation. In n-tuple notation, this structure is alpha 1, alpha 2, alpha n, and when I make this structure like this, which is in dual space, it will convert it to something like this. So, that means essentially what I am doing to go from normal vector space to dual space, that I am changing this structure. This is a column matrix, I change this to row matrix, that means I make a transpose of these things. Not only that, I am making the star of this, that means complex conjugate. So, now just give you some example. So, another important thing we find is alpha beta is equal to beta alpha star. They are not equal in general, they are related to the star when these two are not containing not the real coefficient, rather they are containing some kind of complex quantity. So, then this star will be playing the role, which is important, which is conceptually very important. So, now alpha, just do some exercise 1 1 0 and beta is 2 0 1. If this is the two vectors and if you are asked to make a scalar product or the inner product, then I will have this alpha beta. Alpha beta is just according to my rule, when I make alpha here I need to change the structure like 1 1 0 and this will remain unchanged because I am using these things here, it will be this, and as a result what I am getting 2 into 1 2, 1 into 0 0, 0 into these things. So, it will be essentially 2. Now, if I do the way I do last time, just rotating these two vector alpha beta, instead of doing alpha beta, now I am doing beta alpha. So, then now beta I need to rotate, so 2 0 1 and then 1 1 0. Again if I multiply this into this 2 0 and 0, I will have 2. You can note that alpha star alpha beta this inner product and beta alpha this inner product, both are giving the value 2, the same value, because these things containing the coefficient which is real in nature. Now, change this coefficient to complex and just check whether this is following these things or not. This is I need to check. So, say alpha is I 1 say minus 1, beta is vector beta is say 1 I 2, whatever the value you want you can put. Then alpha beta, how do I write this? Alpha I need to rotate it, so it will be minus I, because when I rotate this I need to put the complex conjugate of these terms. So, I should be equal to minus I 1 minus 1. B will remain unchanged because I am not doing anything over beta. Beta is not going to change. So, now what will be there? It is okay. Now, I am taking the example in such a way that this becomes something real actually. Okay, so go with that, then I will change that. So, I multiplied by 1 is minus I, and then there is a plus I which is absorbing the thing. So, now I will have minus 2, I have real thing. So, expect it that when I do beta alpha, it will not going to change. I 1 and minus 1. If I do, then I sorry, when I make a change, here should be a minus 1 because I am making the beta vector into I am making a dual conjugation of beta vector. So, the coefficient. So, again I multiplied by I minus I, and I will again come, it is boiled down to a value minus 2. So, there will be no change because these and these are both are real quantity. So, it will, I mean, that is why alpha beta and beta alpha become same. Now, if I change, now I need to change because so make it as 2i. Let us check whether by putting a 2i I am getting something extra or not. So, what will be my alpha beta? Alpha beta will be minus I 1 minus 1, and it is 1 2i 2. What will be the result here? This is, let me calculate meticulously. This is minus I, this is plus 2i, and this is minus 2. So, what will be my result? My result is I minus 2. I am getting a result I minus 2. This is a scalar quantity, even though this is a complex, but this is a scalar. So, this is a scalar thing that is valid. But now I am going to do the other way, I will change that. So, then I need to write it 1 minus 2i 2 multiplied by alpha, which is I 1 minus 1. Again meticulously, if I calculate, then first term is I, second term minus 2i into 1, which is minus of 2i, and third term 2 this. So, minus 2, which is minus I minus 2. Now, you can check the difference, you can see the difference, that initially it is I minus 2, now it is a minus I minus 2. The meaning is that alpha beta is nothing but beta alpha star, which have already shown in general way. So, just this is a just merely some example to show how this inner product you should calculate, and also you should note that when the elements are complex, so there is a rule or there is a property that these two things are equal to each other with this relationship. Okay. So, now with that also we can prove or we can show few things. So, let me do that straightway, that now I know how to calculate the inner product, which is not a very new concept to you, but still the way the structure is presented here may be something new to you, that is dual concept of dual space and all these things. So, let me just check few things, that I am saying that E1, which is 1 0, and E2, which is 0 1, is a natural basis and orthogonal to each other. So, they are orthonormal. So, that means this quantity readily we will check, this is a quite straightforward thing, but it is important that what is going on here. What value I am getting? This, it is 0. That means whenever I change 1 and 2 and this coefficient is changing, it is not the same coefficient, I am having 0 in my hand. So that means they are orthogonal to each other. The first thing, they are orthogonal. The next thing is that I will do the same thing, but I am changing E2 to E1. I am making an inner product of the same quantity. So it will be 1 0 and it will be also 1 0. So what I am getting is 1. So that means when two vectors are multiplied to each other in an inner product notation, I will have a scalar quantity. If the scalar quantity is 1, I can say the norm of E1 is equal to 1. Norm is the root over of these things. This is 1. So if I make a root over of these things, so this is 1. In the similar way, you can show that E2 will be 1. So the conclusion is, or not, it shouldn't be the conclusion, I should say that whenever I am taking the natural basis, it is following the orthonormal property straightway it will be following the orthonormal property. Now if I change this basis to some different basis, because you should to remember that you can construct in principle infinite number of bases in 2D or 3D or ND depending on the value of the vectors. Only necessary criteria is that in order to form the basis they should be linearly independent. Since they are linearly independent, they are forming a basis, but not only the basis is important, also important their relationship, the relationship between the vectors that is forming the basis. So here we find the relationship is ortho, they are normal to each other, that means they are orthonormal. Not only that, their amplitude is 1, so that is why we say this is orthogonal to each other, orthonormal to each other, that means normal amplitude and orthogonal. So two property together, so they are orthonormal. So now I will going to change these things to some other values, say 1 1 minus 1 1. This is also a linearly set of a linearly independent vector in R2. Now if they are linearly independent in R2, the question is there, what is the relationship between E and E2? So let us just find out. So if I find E1 E2, it will be 1 1 minus 1 1. One multiplied by 1 minus 1, 1 multiplied by 1 1, so minus 1 plus 1, it is 0. I need to check the way around E2 E1. So E2 E1 is whatever the value I have, the complex conjugate of that. Here I have 0, so I don't need to calculate, I can say this is safely 0. Two vectors E1 and E2, when I make an inner product, I will getting the result 0. That means they are orthogonal to each other. No problem with that. Now the question is, if they are orthogonal, so what is the difference between these and previous vector, the natural basis we mentioned? What is the difference between these two? The difference is the norm. So let me calculate the norm. So I will change that E1. So I will make these things 1, and then what is the value I have? I will have value 2 readily. So that means these two has a norm E1, the norm of E1 is root over of 2. In the similar way, if I calculate E2, I also find that this value is 2. So norm of E2 is also root over of 2. So, even though they are orthogonal to each other, but they are not orthonormal, they are orthogonal to each other, that means the angle between these two vector is 90 degree or whatever, because the inner product gives me 0. So, we in general we say this as the orthogonal property, but the norm value of these individual vectors are not equal to 1. So, that means they are not normalized, they are not normalized. So, in general they are not orthonormal, even though they are orthogonal, they are not orthonormal. So, now let us give a very simple example of another vector, say E1 is 1 0 and E2 is say 1 1. These two vectors again, these two vectors are different, and again these two vectors are linearly independent to each other. You can check that they are linearly independent. If I cannot write E2 in terms of E1, which I cannot have, so then these two vectors is a linearly independent vector. So, that means they can in principle form the basis, but what is the difference between these things and previous two? Let us check. E1 E2 1 0 1 1, it is 1. First time we are getting that E1 E2, which is two different vector, when I make an inner product it is not equal to 0, it is 1. That means they are not orthogonal also, not orthogonal, because this is not equal to 0. If the inner product between these two vectors is not equal to 0, which is in this case it is 1, they are not orthogonal. What about the individual norm of this? So, E1 E1, this we have already done. So, this is 1. So, the norm of E1 here is 1, and also if I do these things which we have done in the second example, I will find this is 2. So, norm of E2 is equal to root over of 2. So, these two are forming basis, that is the first case. Second thing is that even though they are forming a basis, they are not orthogonal. When they are forming a basis, you need to understand that a vector in principle can be divided into, can be represented in terms of this basis. There is no such issue with that. So, there will be no problem that a vector cannot be represented in this case. So, it can be represented. The thing is that they are not orthogonal, neither they are normalized. This unit vector, this vector is normalized, we call it a unit vector, but this vector is not normalized. So, in order to normalize, normally what we do, we just multiply this with his 1 by norm. So, then this become normalized. So, if I want to make this vector normalized, so I will change this vector by multiplying this. Now, if I take a new vector which is the multiplication of this vector with its norm value 1 by 2, the norm value, then this vector essentially be a normalized vector. That is the standard way to make a vector normalized. But important point is that even though they are not orthogonal, even though they are not normalized, one of them is normalized, but in general you can expand a vector in these two linearly independent vectors. But there is some problems, because you can't readily, it is very difficult to find out what is the coefficient. That is a different issue, we will come to that later. Okay. So, after having this, so let me, now we know what is the inner product and all these things. So, let me write down one thing. So, alpha and beta are two vectors. So, what is the inner product between alpha and beta? Alpha beta is the inner product, is a scalar value. Now, this scalar value, mod of this scalar value rather, is always less than equal to the individual norm of this. So, this is the rule, this is the relationship between these two vectors always follow, that if I make an inner product of two vector and then try to find out what is the norm of that. Norm means what is the magnitude of that value will be always less than equal to if I take the norm of that individual vector and then multiply it to them. This inequality is a famous inequality, is called Schwarz inequality. Schwarz inequality. Schwarz inequality. So, quickly let us try to prove this inequality. So, try to prove this inequality. So, let me do that in this way. I need to prove this. So, let me construct a vector gamma which is a linear combination of these two. So, alpha plus some constant c beta. This constant c is a scalar quantity and I put c as a plus ib, a complex term. I can put that because this is a scalar. So, scalar can be real and complex. For the time being I am putting is a complex. So, now if I do, then if I calculate these things, so what equation I should write quickly? This plus c star b multiplied by alpha plus c b. Mind it, c star will be a minus ib, which is, if I write expand, which is norm of alpha square, because I make this multiplied by this, then this multiplied by this is plus c star b alpha plus c alpha b beta, c multiplied by alpha beta, and finally this into this, there will be 4 term. So, finally I will have mod of c square into the norm square of beta. This will be my expression. In the left hand side I will have this. So, this is essentially the norm square of this quantity, which depends on the value of C1 C2, because C1 C2 is something which containing AB and this AB is according to my choice. So, I can change the AB in such a way that I can manipulate this quantity. When I manipulate this entire quantity, I can manipulate the value of this. So, I want to make this value as small as possible. So, the minimum condition is this. So, in order to find the minimum condition of what is the value of this minima, so I will try to make a derivative, and this derivative equal to 0 gives me the minimum condition, that is the usual. So, when I make a derivative with respect to a, this is 0 because there is no a. So, this term will be simply beta alpha. The second term will be plus alpha beta, because when I make a derivative with respect to a, c is a plus ib beta ib, and when I make a derivative with respect to a, the a term will be there, the other term will not be there, the partial derivative is there. So, I will get this plus mod of c star. So, mod of c square means this multiplied by this. So, it is essentially a square plus b square. So, when I make a derivative with respect to this, I will have 2a of b square. Now, I am saying that this is 0, for this term has to be a minima. For the minima of this quantity, if I make a derivative over a, then this term has to be 0. So, this gives me an expression of a, which is a is equal to minus of beta alpha plus alpha beta divided by 2 of beta square. This I can do the same treatment for b also, because b is another variable that I put in my equation in through c. So, if I do that, then the first term will 0, but the second term will have a negative sign because it is a c star. C star is a minus ib, so that means this I will be there. So, minus of I b beta and then alpha plus I then alpha, the ordering is important here, beta whatever we have, plus 2b, a similar kind of expression with one I having here. So, this gives me the value of b. I should say this is minimum because I try to find out the value of a and b in such a way that this quantity become minima. So, that means it is a specific value, because it is a specific value I put a term minima here. So, now if I do, then I will find that this is I multiplied by beta alpha and then minus of alpha beta, because I am taking this that side, divided by 2 of mod of beta square, norm square. So, now I have a and b separately. Now, I have a and b separately. So, these a and b now I am going to put here to make it minimum. So, now I am trying to find out what is the minimum value of this norm. This is essentially this quantity. So, if I do, then it will be this quantity minimum, because I am putting the a and b the value that I extracted, which is the condition of minimum. So, this minimum value is essentially alpha square plus c star. C star is containing this and this. So, what is the c star? C star is the minima of this and this if I construct with a plus or ib. So, let me construct it here, it will be easier. So, let me put my C minima. C minima is A minima plus this, A minima plus I B minima, which is, if I multiply I here, so it will be minus of beta alpha plus alpha beta, then I multiply I with this quantity. So, I there will be a negative sign here, beta alpha, and this minus alpha beta whole divided by this quantity 2 this. So, now you can see that one value will going to cut this alpha beta, which is a negative sign, and this is a minus sign, and the plus, this minus will be a plus sign. So, this alpha beta will not be there. So, finally, what I will get is minus beta alpha divided by this quantity. So, this is my C minimum. When I make a C minimum here in this equation, then I need to multiply that. So, this will be minus of beta alpha multiplied by beta alpha, because already one beta alpha term is here. By the way, I need to make a star here. So, when I make a star here, this should be star, it should be star divided by beta square. Then I will have another term which is C. So, C is simply minus beta alpha multiplied by alpha beta and finally I have mod of C square and these things. So, mod of C square is plus that mod. So, mod beta alpha square divided by these things, because 1 it will be to the power 4, but 1 beta square is sitting here. So, it will cancel out. So, finally, I will have. So, now this quantity and this quantity will cancel out, because this is mod of this square, this is also mod of this square. So, I will cancel out this quantity. So, this is cancel out. So, finally, what I am getting essentially is a simple expression. So, quickly let me show that what I am getting is gamma square minimum is equal to alpha square minus this quantity which is beta alpha multiplied by alpha beta divided by mod of norm of this square. So, now this minimum value we already explained the fact, we have already explained the fact that this value has to be greater or equal to 0. This value has to be greater or equal to 0. Now, if I apply these two things, then readily I will find that this is greater or equal to this quantity. This quantity is nothing but mod of alpha beta square, because alpha beta star is equal to beta alpha. So, if I change this to star, it will be beta alpha and mod of square. So, it is alpha beta mod of square and beta alpha mod of square will be the same thing. So, essentially I am having this. So, from this expression I readily can say that alpha beta is greater than equal to this quantity. So, we prove one very important identity which we call the Schwarz identity, which is this, that when we are calculating the inner product of two vectors, this is the inner product, the mod of the inner product of two vectors is always less than the individual norm of the two vectors when they are multiplied. So, with that I would like to conclude today's class. So far we learned few important concepts regarding the inner product and how it is formed, and all these things. In the next class we will try to start to finding out how to form these bases, because we will now going to play with the bases. If a set of linearly independent vectors is given to you, can I make this set of a linearly independent vector to a basis which are orthogonal to each other? This is a very important aspects to form a basis, and we always use this kind of, because we always want the basis to be orthogonal to each other and normalized. So, we in general we always try the basis to be orthonormal to each other. So, we need to find out what is the procedure that I can make a orthonormal basis. So, next class we will start from here and try to find out what is the procedure to make these orthonormal bases. So, with that, so thank you very much for your attention. So, see you in the next class.